Assalamu alaikum warahmatullahi wabarakatuh everyone. Today inshallah we will solve problem 12 from chapter 3. And the question says in the mechanical system shown in figure 342, assume that the rod is massless, which is this rod, okay, perfectly rigid and pivoted at point P. The displacement x is measured from the equilibrium position, and assuming x is small, so this means that sine theta will equal theta and cosine theta will equal simply 1, okay, and that the weight mg at the end of the rod is 5 newton, and k is, or the spring constant, is 400 newton per meter. Find the natural frequency. The natural frequency, if you remember, is k equivalent of the system over m equivalent of the system, or simply k over m. Okay, so to find uh, the natural frequency first, we need to find our or we need to derive our equation of motion. So to derive our equation of motion, first we need to identify our degree of freedom. In this system we have only one degree of freedom, which is theta. Okay, so we will use that as our degree of freedom. Okay, so just let me try to draw this one. Okay, so here we have our B, and our system will be displaced like this or rotate like this. Sorry. Okay, and like this, and it will be like this. So this is our movement or displacement x. This is our, or originally our 2a, and this is originally our a at the equilibrium position. Okay, now, so again, what we need to do is to put the forces in our system. First we will start with the spring, and as you can notice our system rotated clockwise. So if you need to replace any spring or damper with a reaction force, you need to make sure that this force will be opposite to your motion. Either, for example, if your motion or if your system is moving to the right, the force reaction from spring or damper should resist this movement, so their direction should be to the left. The same if your system moving up, their direction should be down. And if your system rotating clockwise, your reaction forces from the spring or the damper should rotate your system or resist your rotation clockwise, and should be rotated counterclockwise. I hope this is clear. Okay, okay. Now now what is the force that, or what is the direction that could help us to make our system resist rotation in clockwise? It is in this direction. So our key x2, which is here, okay, we multiply by x over 2 because this is our degree of freedom. Okay, in this location, it will resist the movement of our system in clockwise direction. Okay, now let's come back to the weight mg. Here is two tricks, okay, or one trick to determine whether to consider mg and put it in your system or not. If you take mg or take your weight out of the system, and the system change, for example, the spring come back to its original position, because as you can see here, if I put the weight, the spring will be stretched, right? But if I remove the weight, the spring will come back to its original position, right? So if that happen, you need to or you don't need to consider your weight mg. But if you remove the weight, for example, and nothing changed, then you need to consider that weight. Okay, so here in our scenario, if we remove the weight, the spring will come back to its original position. So the conclusion is that we don't need to consider the weight. Okay, so our equation of motion will be the summation of torques or moments will equal to g or j theta double dot. So the only force that is doing some torque or moment is kx over 2, or the spring reaction force. And before putting this force, we need to know our conviction. In this system, to know your conviction, just always go with how your system is moving. If it's moving to the right, then your conviction or positive direction is to the right. If it's going to the left, then your positive direction is the left. If it's rotating clockwise, uh, this is your positive direction, and vice versa. Okay, so here our system is moving clockwise, so our convection is counterclockwise. Okay, so this kx over 2 is doing a torque in the clockwise direction, so it will be negative. So minus kx over 2 multiplied by the horizontal distance a, okay, and plus or there is no plus, and equal j theta double dot. Okay, now the question says that we need to convert, or we need our equation of motion to be in terms of x. So this means that we need a relation between x and theta, right? And this relation we can get it from this, wait, this relation we can get it from this beautiful triangle. Okay, so we have, and we have the our half of the beam, sorry, we have this one, and we have b here, and we have our beam or rod. Okay, and we have here the distance moved by our rod, which is x. Okay, and we have here theta, and this is, sorry, this is 2a. So you have everything. So sine theta will equal to x over 2a, right? And from before we said that sine theta for small displacement x is equal to theta, right? So theta will equal to x over 2a, and that's it. This is how you convert from theta to x coordinate. Okay. Similarly, we for theta dot, it will be x dot over 2a, and for theta double dot, it will be x double dot over 2a. And for j, we will treat this scenario as a pendulum scenario. So our j in this road, or for this road, will be ml square, and our L is 2a, so it will be m or 4ma square. Okay, so plugging back the equations, we will have minus k x over 2a, or sorry, we will have 4ma square multiplied by x over 2a plus, sorry, plus x double dot plus kx over 2 over 2a equal 0. Okay, now multiply both sides by 2a, we will have here 4m, uh, here, yes, we'll have here 4m8 square x double dot plus k x, or k a square x equal 0. Now this is our k equivalent and this is our m equivalent. So n will equal to square root of k a square over 4m a square. We will take that out and we will lift up with k over 4m, which is which is or the m, it will be weight over g, and our will equal to 400 over 4 multiplied by 5 over 9.81, and this will equal to 14 radian per second. Thank you guys and good luck.